We are going to have three presenters speak to us now, and they are going to address the issue of smarter green cities and transport technologically enabled by multimodal collision avoidance systems. So I would like to welcome Sascha, Ricardo and Jason. Good morning and thank you for joining us. Simon, I think, Sascha, I think we're starting with you, is that right?
Yeah, we can, absolutely. Good morning, Annie. So we have a panel discussion this morning, and I'm going to start the whole thing. We're going to talk a little bit about what you can do on the edge when it comes to the future of transportation and when it comes to transportation safety. For that, I'd like to screen share. Let's see if that works. And here we go. Yes, wonderful. Great. So my name is Sascha Simon. I'm the founder of Sfara. Sfara, you may not have heard of this company yet. We are a startup providing mobile artificial intelligence solutions to enterprises in the space of transportation and safety. Our customers are ranging from the OEM world, like Daimler is one of our customers, to the insurance world. And we primarily have solved safety detections on mobile phones. So while we do that, we, over the past year, have come across the potential and opportunities that arise if you combine mobile detections with a super fast 5G edge network, and are in the process of developing something that I want to share with you this morning, which I personally find incredibly exciting, which is really turning smartphones into what we call intelligent beacons to protect people from accidents in a future transportation world where we have a mix of fully autonomous systems, partially autonomous systems, and no autonomicity at all. And in that universe, we do have something that we call vulnerable road users, which we consider everyone that really doesn't have a crumble zone or a crash protection around themselves, right? So the idea came up, what could we do if we have the ability to utilize smartphones to detect that, let's say I'm a pedestrian and I'm walking down the street, or I'm on a bicycle, I'm in a car, and if I have the ability to really project my trajectory a couple of hundreds of meters ahead, and if I could share this information with the other traffic participants around me. Well, for those of you working in that space, that sounds an awfully lot like V2X, vehicle to infrastructure. Well, that's exactly what it is. It's in that space that's called CV2X, cellular vehicle to infrastructure. With one wonderful advantage, we're utilizing a ubiquitous technology. We're utilizing smartphones. We're utilizing edge computing, 5G networks. So while CV2X is kind of a holy grail of cities and municipalities to bring down accidents, we're utilizing a technology that is really in everyone's pockets to make that happen, meaning there's really no additional hardware that everyone would have to have, except utilizing a good amount of artificial intelligence in the system to make that all happen. Now, if you look a little bit at statistics, then we see that in 2018, that's the numbers I have, there were 23,000 people killed in Europe alone, according to OECD and Eurostat. And on bicycles particularly, we had a 16.5 increase in fatalities, and on small motorcycles or mopeds, we have a 32% increase in fatalities, primarily between vehicles and these two-wheelers. Now, the image that you see here in front of you is kind of setting the stage for the coming discussion here in the next couple of minutes. And on that image, you basically see a bicyclist and a vehicle. The vehicle wants to turn right, doesn't see the bicyclist. The proverbial blind spot detection here is failing. And normally that would be an accident. Now, if we would have the ability with a super low latency to warn the vehicle and maybe the bicyclist, depends, then we could avoid that, right? We could also inform the vehicle that there are pedestrians about to cross this intersection that you see there, meaning either warn the driver or somehow interact with this vehicle to actually slow down if it enters the intersection. That would be really fantastic. And many of you in the industry have seen these scenarios a lot, primarily based on automotive industry, new technologies in the space of autonomicity. The problem is that in these scenarios that involve the cars, they only involve the cars, but they are not only cars on the road. And so the advantage of utilizing smartphones is, I think, a given here. We call the whole thing Mcas, that stands for Multi-Modal Crash Avoidance System. And it's really employing a couple of players working together. And the most important two we have on the panel today. We have Ricardo Gomez-Ulmke from Solace and Jason Hoffman from MobiledgeX, who are working with us on this new, I think, very exciting technology. And with that, I would like to hand over to Ricardo. Ricardo, the floor is yours.
Thanks, Sascha. Good morning, everybody, and thanks for having me. Yeah, as Sascha mentioned, we've been working on this system for a while, probably about a year now. And one thing that I want to point out, and something that we've come across very early on, was really the latency challenge, right? So just to give you a couple of ideas to put that into context. Let's assume we have an intersection with 4 cars and 1 pedestrian that is trying to cross a street, and there's a potential collision course, right? So, car coming from left and right, and the pedestrians trying to cross the street, and we want to detect that. So the challenge that we set ourselves and the way that we designed our testing and everything was to say that within 100 milliseconds, we want to be able to gather all the data, i.e. the projected trajectories from these participants, and then within 100 milliseconds, be able to send out warnings, alerts, or as Sascha mentioned earlier, potentially even stop commands to the cars itself. Right, why 100 milliseconds? At a speed of 50 kilometers an hour, within 100 milliseconds, the car travels about 1.4 meters. So that is, that's a steep goal. Now, in terms of the 5G networks, obviously, the latency is already a lot lower, right? So we've heard from KPN earlier today, network latency is about 20 milliseconds. Right. And then the next thing that we need to consider is that these cars and the pedestrian, they're possibly not all connected to the same carrier, right? One might have a SIM card contract with carrier 1, the other one's with carrier 2. So that means that potentially we're looking at 2 different edge locations or edge cloud locations that need to be combined, and the messages or the events coming from these smartphones or from the intelligent beacon needs to be, the event stream needs to be combined into one single AI engine. So that means that the next level, it's really the event distribution. And that is what we've been trying to tackle. So, we have 20 milliseconds from the 5G network. Event distribution perhaps adds another 5 milliseconds. So that means 25 milliseconds of the 100 milliseconds are gone. So now that leaves us, though, with enough space in the latency orchestration for the AI to do its thing, right? And now the next consideration that we then made was, that's a very tiny intersection, 4 or 5 participants. A normal intersection, let's look at one that maybe has 100 participants at any one point in time. So that means in terms of the number of messages, it's, we're looking at around 280 messages a second just to manage a small intersection with 100 participants. But of course, we cannot deploy one solution for each intersection. So we have to create, sort of a geozone. And perhaps these geozones control 100 or 1,000 of these intersections. And so all of a sudden, what we're trying to achieve here is this 100 millisecond goal at scale. And that, in our calculations and our tests resulted in being able to manage about 3 to 5 million messages a second. And that is one, that's sort of the challenge that we call critical latency orchestration for temporary co-located participants. So there you go, that's another buzzword for you.
Just the only thing I can really add to this is just a bit about, this is a good illustration that Edge is an embedded application environment present within mobile networks themselves. And now that we actually start having an embedded application environment on devices, we have one present within mobile networks, we have one present within the internet, which is what the public clouds are. That actually having these 3 things work together very well is important. Right now, it's largely smartphones connected to mobile networks, which then connect to consumer and some enterprise-facing applications sort of present on the cloud. Those are the ones that have the largest sort of bulk thing out there. And when you start sort of thinking about this idea that every use case in the future is going to have a device connected to an edge that connects to a cloud, there's the basic question of really what are sort of the large, still sort of emerging use cases? What's the type of device that a lot of people are basically interested in? And then as you begin to connect those types of devices and coordinate those types of devices, what types of things are people going to be really interested in as a result of doing that? Of course, cars are a very good candidate for a dominant device besides a smartphone. Most people have a smartphone, also have a car. And you can't crash your smartphone and die in it, but you can crash your car and die in it. And so it's a device then where the use cases around it become, important to human health and well-being. I think efforts like this are very challenging to achieve within the industry. As you said, having multiple edges, multiple providers, multiple sort of this, but provides a good candidate for large scale type use cases that'll really sort of stress the edge and the underlying infrastructure to its utmost.
Okay, so could you just explain a little bit more about the role that MobiledgeX Edge is playing here? Presumably you're about collating, collaborating, bringing the operator end of the deal together. Is that correct?
Well, that's one part of it. I mean, we were created by Deutsche Telekom back in 2017 to, of course, first and foremost, be able to surface up this embedded application environment within networks themselves, also known as the edge. But when we looked at like what Ricardo was talking about, where you have cars from different manufacturers, edges from different network providers, you have multiple cloud providers. So if you just think about the possibility that something can be sitting on top of Amazon, Microsoft, Google, IBM and the like, they could be across sort of 5, 6 different car manufacturers, and they could be connected to 2 or 3 sort of dominant sort of mobile providers. The thing that we've always then sort of dealt with is exactly all the integration points and that type of heterogeneous orchestration that has to occur across that. So we end up really sort of sitting as this multi-device, multi-edge, and sort of multi-cloud orchestration layer that provides a consistent application environment across really sort of all those sort of emerging endpoints.
Won't Mcas be obsolete once we get more autonomous vehicles? I don't know, Sascha, that might be one for you.
Yeah, that's a good question. Thank you, Annie. Well, absolutely not. I think it's going to be even more important in the world of autonomicity, because autonomous vehicles have to share the road with human beings. I don't think there will be an autonomous bicycle, put it this way, or autonomous pedestrian. So it is that proverbial ability to, quote unquote, look around the corner that's really critical here. So autonomous systems obviously have to be interconnected and have to have the ability to see around the corner to avoid potential impacts. And that works wonderfully if the other participants are autonomous systems too, right? But they are not sometimes. And that's exactly where you need a system that connects all traffic participants in this world. And why not utilizing that system based on existing infrastructure, meaning the mobile phone and the edge networks, the edge clouds, to make that happen? Because otherwise you would have to have some sort of a transponder type of device that you give to bicyclists. And there's lots of research also by the Technische Universität Berlin made in that space, where they show that it all works wonderfully if everyone carries a little, device transponder. I don't think that's going to happen, but you're already carrying a type of transponder, and that's a smartphone. So I think that's critical. And I also wanted to add a fourth team player here in this Mcas universe that I didn't mention in the beginning, and that's obviously Exedion. Because there's one part that is critical here, which is that we have to have the ability to ensure that the data stream that is shared between all these participants in traffic is validated and is secure. And we're talking safety of lives, we're talking decisions in milliseconds, and we have the company Exedion, who is also a sponsor of this conference here, part of this whole universe as well. I forgot to mention that in my starting speech. Hopefully I was able to answer that question, Annie.
There's been a couple of questions around data and privacy, and who owns the data,
yeah,
and who manages the data and all that, which I guess is quite tricky, because
absolutely,
and a lot of data as well. Yeah,
no, that's a really good one. I'd like to hand this over to Jason and Ricardo as well, because I think that's a really critical point here. And that's where we put a lot of thought into the architecture of this whole thing. So the artificial intelligence that basically identifies that you are on a bicycle or in a car or in a train or whatever, and that calculation of your trajectory within the next 50 meters, within the next 100 meters, is really done locally on the device. And I think that is a critical differentiator. So as long as it's on the device, right, you own that data. It is your data. Now, that data, to a certain degree, will go out to the edge cloud. But the edge cloud, again, is owned by the carrier. That would be Jason, right? So the carrier has already your privacy information because you're a customer of the carrier. And from there, it doesn't go anywhere else. It just goes right away back to the other traffic participant with a warning. So that basically combination of information from, let's say, the traffic participants in an intersection happens in the edge cloud. Doesn't go anywhere from there. And I think that's a critical differentiator here. We're not pushing this into anonymous Google Cloud or Amazon Cloud or IBM Cloud or whatever cloud. It really stays locally. Jason, maybe you want to jump into that.
Yeah, I mean, we have, as you said, we have precedents in the space already, and that is that if you put a dongle in your car today, one of the challenges that even insurance companies have had around accessing that data and doing things with it is that every car manufacturer and sort of precedent in the industry is that you as the car owner own that data, you as the driver of that car own that data. I imagine as long as there's a human driver behind the wheel and the human, owns that car, that sort of mentality will sort of remain the case. Now, then when you look at Edge and a lot of the Edge APIs that we've developed, all the concepts around data sovereignty, privacy, data locality, or concepts that are built into those types of data services. So there are different types of consent loops in that system where an end user can actually give consent and withdraw consent and sort of take care of pretty much any data element that they would basically like. There's a lot of features available to developers, if you will, around privacy and data sovereignty to sort of ensure that sort of pipeline. And in a lot of ways, those privacy features and data sovereignty and data locality features is really one of the core differentiators in Edge services.
Okay, we've got a couple more questions, but we will have to be quick, please, Mcas. We're a little late. So Dean asks, what happens with Mcas where users have VPNs with distant egress points or have phones attached to Wi-Fi, which, as he points out, can be up to 80% of the time? How does that play in this scenario?
That's a good question. Maybe Ricardo, you want to jump in on that one?
Yeah, I mean, of course, I mean, if the mobile phone does not have a 5G connection or no connection or path to the telco edge, there's not that much we can do about it, right? So, but on the other hand, if you think you are in a car and perhaps that has a Wi-Fi hotspot, that Wi-Fi hotspot again is actually connected via 5G.
Okay.
So it's just a hop, really. So I don't see.
I think the basic answer to that is, like when we go and put SDKs in there, we're taking over routing, name services, and sort of functioning as in the middle of an encrypted stream. And if somebody decides not to participate in that, then none of this will work. So, yeah.
Okay. Just
but that's an end user saying no, thank you.
Okay. Just one really quick question. How is Edge Mcas better than a car-based solution?
Yeah, very simple. The car-based solution works for the car, not for the bicycle.
Or the pedestrian, or the person pushing a pram or in a wheelchair.
No, but the general thing on this is why not just do everything on a device? Or that, and the thing is the second you have a population of devices and you have heterogeneous devices, and you can say that those are different generations of the same smartphone from the same manufacturer, or it can be a bike versus a car. But the second you actually have more than one device, and the second you have like more than one type of device, then you actually need another layer of things to actually coordinate that population. It's just that simple.
Okay, so thank you. Basically, this is about using the ubiquity of mobile phones, really.
Yeah.
Okay, thank you very much.